Today we'll be discussing volume. So let's consider cylinders. How do we find the volume of a right circular cylinder? Well, a right circular cylinder has a base that's a circle. Okay. And then the top is parallel to the base. And if we wanted to calculate the volume of this, then we have pi r squared h, where r is the radius of the base. Now let's think about where this formula would come from. Pi r squared is the area of the base of the cylinder. And then we multiply it by the height. So what do we do about more complex cylinders, which are not necessarily right circular? This is still a right cylinder, but it's not circular because the base is not a circle. It's right because the sides are perpendicular to the base. Okay. Well, we could determine the volume by finding the area of the base and multiplying it by the height. Okay. So this will work for any cylinder. So let's let A of y be the area of the base. Then the volume would be equal to A of y times h. Okay, in this case, the area of the base is the area of any cross-section perpendicular to the y-axis. So what does it mean to have a cross-section perpendicular to the y-axis? Well, if we have the y and x axis, a cross-section is just a slice through this cylinder. Okay. So a cross-section is like if you slice it, okay, then you'll get a cross-section right there. Okay. And it's perpendicular to the y-axis. If one were going to be perpendicular to the x-axis, then that would be a vertical slice like this, right, which would look, in this case, like a rectangle. So what happens if we want to find the volume of an irregular solid, or a solid that is not a cylinder? So let's consider this solid, which I'll label S. We can approximate the volume of this solid using cylinders. right? So here we have cylinders where the area of the base of the cylinder will match the area of a cross section at a specific point. So maybe the first cylinder that we're using has a base that has the same area as the top, but then maybe the second cylinder has a base that has the same area as a cross section here, which we'll call at the point Y1. So perhaps at this third cylinder, this little one, we're taking a cross section here, which I'll call at Y2. And we're using that cross section, okay, as the base of that cylinder that we're using to approximate the volume. Well, how would we get this volume, okay, to be a more accurate approximation? Well, we would use more cylinders, and they would be shorter cylinders. Okay. So notice that the height of each of these cylinders is like a delta Y. So we could get a more accurate approximation if we use more cylinders that are shorter. So right now our approximation of the volume is the sum of the volumes of all these cylinders. Each cylinder has a height of a delta Y, okay, and then we'll say A of Y, I, where I ranges from 1 to n, is going to be the area of the cross section perpendicular to the y-axis at yi. Okay. So if we're going to be taking more cylinders to get a more accurate approximation, we might say, well, if we want the exact volume, why don't we let n go to infinity or delta y go to 0? So our exact volume would be the limit as n approaches infinity of this Riemann sum. Okay, well, this looks just like the Riemann sums we were working with before. All right, we have a delta y, and then we have a function of y. So we can calculate the volume of a solid that's extending from y is equal to a to y is equal to b, which in this picture would be the y value of the location of the base of this object, and then the the top of the object would be B. Okay, then the volume of the solid is just the integral from A to B of A of y dy, where A of y is the area of the horizontal cross-section at the height y. So let's see an example of this. So sometimes we may want to, instead of taking horizontal cross-sections or cross-sections perpendicular to the y-axis, we may want to take cross-sections perpendicular to the x-axis. So if we had an object like this, and we embedded it into the axis like this. Now this is a 3D object, so this would be actually in 3D space. So this would be the Z. Okay. So we have an x-axis, a y-axis, and a z-axis now, which we won't be using that, but it's just nice to remember that we are working with 3D objects here. Now we could instead calculate the area or the volume by integrating with respect to x instead of with respect to y, and here you would take cross sections that are perpendicular to the x-axis. And we'll integrate with respect to x instead of with respect to y. So let's look at an example. Let's find the volume of a pyramid with height 8 meters and a square base of side length 3 meters. With a square base, okay, the square base each has side length 3 meters and the height is 8 meters. Okay. So if we're going to find the volume of this, we want to find the area of either a horizontal or vertical cross section. So what would a horizontal cross section look like? Well, we have our pyramid, and we would be taking like a slice of it, okay, at a certain point. And we'll notice if we take that slice, it will look like a square. A vertical cross section, which would be going perpendicular to the x-axis, would be a rectangle. Let's use the horizontal cross sections instead, since it's a square, and now we just need to figure out the side length of this square. Let's embed this into the plane. So we're just going to project it onto the plane. Okay, so now it just sort of looks like a triangle. Okay. Since the base has length 3, right, because it's a square base of length 3, then if we center it, the endpoints of this base, or the edges of this triangle, will be at x is equal to 3 of 2, 3 over 2, and x is equal to negative 3 over 2. We know since it has height 8, the top is at 8 if we're putting it on the x-axis. Okay. So we want to know at any point y, what is this distance here? Well, it will just be twice the x value on this line, right? Because that'll be, we have this distance and then multiply by 2. Okay, so if we can figure out the equation of this line, we can figure out the x value for that's associated to any value of y. Well, the slope of this line is going to be negative 16/3. Right, we have 2 points, so we can easily calculate the slope. So we know that the equation of this line is y is equal to negative 16/3 x plus 8. So we want to know the x value for any value of y, so we just solve for x. So for any value of y, this distance here, the distance from the y-axis out to the edge of this pyramid, will be given by y minus 8 times negative 3/16. Okay. So the side length of the square, that is the cross section at some point y, at some value of y, will be twice that. So it'll be 2 times negative 3/16 y minus 8. And we can simplify that to negative 3/8 y minus 8. So this means, so a of y, which again is the area of the cross section, for any value of y, so in this case, y will be between 0 and 8, will be negative 3/8 times y minus 8 squared. Because it's a square, right? We know the side length, so then we know the area. So the volume will be the integral from 0 to 8, right? Because the bottom, when we put this onto the plane or projected it onto the plane, we put the bottom of it at y is equal to 0, and the top of it is at y is equal to 8. So the volume will be the integral from 0 to 8 of a of y, which is this negative 3/8 times y minus 8 squared. And now we can just integrate. First, let's simplify. So we'll have 9/64 times y minus 8 squared. And we can rewrite that y minus 8 squared as y squared minus 16 plus 64. So we have 9/64 times y cubed over 3 minus 16 y squared over 2 plus 64y, evaluated from 0 to 8. We get 24. Using the formula for the volume of the pyramid, we can check the volume should be equal to length times width times height divided by 3. In this case, the length and the width is the same, so we should have 3 times 8 divided by 3, and we get 24. So we have computed this correctly using integrals. And in fact, you can use the integral, like you can use the method of finding the volume using the integral to actually show that this formula is true.